Hi, my name is Hazim and today I'll be talking about ordered differential equations, its history, theories, and applications, along with a few examples. So, what's a differential equation? A differential equation describes the relationship between several variables and the rate of change of differential in one variable. So, to begin with the history of ODE, since its introduction in the middle of 17th century, differential equations have been a significant area of pure and practical mathematics. Leibniz and the Bernoulli brothers and others first developed differential equations in the 1680s, not long after Newton developed fluxual equations in the 1670s. So now what's the ODE theory? The ODE theory states that the highest order derivative that a differential equation has is used to define the equation's order. The highest order derivative of a differential equation is defined as its degree, which is expressed as a power. If the function and all of its derivatives occur to the first power and the coefficient of each derivative in the equation solely concerns the independent variable x, the equation is said to be linear. Various forms of ODE exist, such as linear and nonlinear, homogeneous and non-homogeneous. A few applications of ODE in the field of biotechnology are: there are many biological laws and relationships which can be expressed mathematically as differential equations in molecular biology mathematics. Ordinary differential equations are formulated as expressions of time evolution of concentrations of molecular species in the vast majority of cell and molecular biology models. This equation describes systems with a large number of participating molecules of each type, given that diffusion is high enough for spatial distribution of molecules to be homogeneous. So now let's move on to a few examples of ODEs. So to begin with, a separable ODE. As you can see, a separable ODE can be written by the following form. An example would be mentioned below is dy over dx equals to y plus 3x squared times y. So we differentiate this in terms of y and then separate it by moving dy over y to a side and the x coefficients to another side where dx is present. So if an ODE is not separable, we might need to make it homogeneous in order to separate it. A homogeneous function is if the nth of every real lambda is same or equal. For example, as you can see over here, the the function x squared plus y squared equals to the below solution has a degree of 2. So we can say that lambda is lambda power is to the degree of 2, and hence we it is a homogeneous equation. Yeah. So now let's move on to linear ODEs and non-homogeneous linear ODEs. If a function of a following form below is present, then it's a linear ODE. For example, y prime plus bx times y equals rx. An example is mentioned with a solution below where we find the y prime in terms of c, the integrating constant. An ODE is said to be homogeneous when the Rx is equal to 0. Hence, we need to find out an integrating factor called fx, or a function, integrating function. And now let's move on to the types of ODE, homogeneous ODE and reduction of nonlinear ODEs to linear ODE function. So, the homogeneous ODE, as I mentioned previously, is when the nth term of every real lambda is same or equal. For example, as you can see, the lambda over here is second degree homogeneous function. So finally, let's move on to the reduction of a nonlinear ODE to a linear ODE. As you can see, we do require this equation to reduce a nonlinear ODE to a linear ODE, and then we do need to calculate the a of y to the power a using the following equation below, which I have mentioned. After finding this, which is ux, we have to multiply this across the entire equation towards the product side and also towards the left hand side and the right hand side. So there are a few more ODs which I hope to discuss in the future. Thank you.